Hi, Algebra 2. In this lesson, we are going to be working on finding real roots of polynomial equations. So everything we've done with factoring and dividing polynomials is going to come together in this lesson. Here we go. A few things you're going to see come up is that we're going to look at the multiplicity of roots. That means that some roots are going to show up more than once. And we're also going to use the rational root theorem and the irrational root theorem to help us solve polynomials. Your first step in factoring polynomials should always be to look for that common factor. It'll make your life easier if you can find it. In this one, our common factor is going to be 4x to the fourth. And as I factor that out, I'm starting to see that I'm going to end up with something that is much easier to work with. And so from here, we're just going to keep factoring. And this second part can be factored as x plus 3 times x minus 2. And so now my three factors are going to be x equals 0, because that's what, if x was 0, this whole thing would be 0. In the next part, if x is negative 3, in this part, then the whole thing is going to be 0. And in the last part, if x equals positive 2, then the whole thing is 0. So this one has 3 roots, and those are it. To solve this polynomial by factoring, the first thing we need to do is set it equal to 0. So I subtracted 26x squared from both sides. This one's a little bit different because I have x to the fourth here, but I know that I can split that up into x squared and x squared. And then we want to end up with 25 on the end and negative 26x squared in the middle. So I'm going to do negative 25 and negative 1 right here. Now I'm going to check and see if each of these pieces can be factored more. X squared minus 25 can be broken up into x minus 5 and x plus 5. And x squared minus 1 can be broken up into x minus 1 and x plus 1. That's that difference of squares coming in there. Again, here we're going to look at each piece and figure out what does x need to be to make each part equal to 0. Because if any of those equal 0, then the whole thing is going to be equal 0 because everything is being multiplied. There are the 4 solutions, or the 4 zeros to that polynomial. In this one, I added 50 to both sides to make sure it was equal to 0. Now I'm looking at the possibility of factoring by grouping. So in this first part, x squared was a common factor, and if I take that out, I'm left with x minus 2. So I'm looking to see if I can get x minus 2 to be a factor over here as well. And so I notice if I take out negative 25, I'll be left with x minus 2, because that's what I would need to multiply it by again to get back to here. And so factoring by grouping did work. Now x minus 2 is a common factor, and I'm left with x squared minus 25. I'm not done yet though, because x squared minus 25 can be factored into x minus 5 and x plus 5. This means that the 3 solutions are going to be x equals positive 2, x equals positive 5, and x equals negative 5. That's what x needs to be to make each of those pieces equal to 0. Here's where we see the term multiplicity come in, and it's going to be the number of times that x minus r, or a certain factor, is a factor of p of x. So if we see that show up more than once, we're going to have a multiplicity of our roots. Sometimes a polynomial just doesn't lend itself to factoring by grouping or by the other ways that we've used so far. So we need to graph it to at least get us started. We can see that there's going to be at least one 0 here at negative 2. So I know that that is a factor. I am going to start using synthetic division now, because I know that negative 2 is a factor. And I'm going to write down the rest of my function using synthetic division. Okay, I end up with this when I did my division. And so I know that negative 2 was a root, so x plus 2 is a factor, because then x would be negative 2 there. And the rest of this is what I would multiply by to get back to my original polynomial. And now I'm looking to keep factoring. So this part, I could factor into x plus 2 times x plus 2. And so here I see that multiplicity. For each of these, x equals negative 2 is the root. And so negative 2 is the root with a multiplicity of 3. So it shows up 3 times. We cannot see that from the graph that we were looking at. We can only see that by factoring it out completely. In this one, I've graphed just to get us started, and I can see that there's going to be at least one root at -3 and at least one root at 1. So I'm going to use synthetic division to start factoring this one out. I've set up my synthetic division with -3 as a root. I saw that from the graph. I did have to put a 0 in here because there's no term with just x. Okay, I did synthetic division. I ended up with this. I got 0 as a remainder, which is good. Next, I saw from the graph that 1 was a factor. So I'm going to start with that now and do the synthetic division. So when I did synthetic division with 1 as a factor, I also got 0, so that's good. So what I have left here is now getting pretty simple. I just have 9 plus 6x plus 1x squared. And so right now, I know that I could rewrite this as x plus 3, that's because -3 was a factor, times x minus 1, because +1 was a factor, times x squared plus 6x plus 9. And I could keep factoring this last part into x plus 3 times x plus 3. And so I see that x equals -3 is a factor with multiplicity 3. It shows up 3 times. And also x equals 1 is a factor, and it only shows up once, so we could say it's multiplicity 1. Next, we're going to see polynomials that might have some roots that are irrational, meaning that they don't come out to be nice integers. They might have some square roots with them. The irrational root theorem is just saying that if an irrational number like a plus b times the square root of c is a root, then so is a minus b times the square root of c. So you get that plus or minus, both being roots. Okay, so getting started with this polynomial, it doesn't look like our regular ways of factoring are going to work very well, so I graphed it, and I'm seeing one root here that is a nice number. It's going to be 1/2. The other roots are not nice numbers, those are decimals, and you can bet that those are rounded, so we're not going to use those. But we can start with this 1/2 as a root. I've set up synthetic division using 1/2 as a root. I did need to put a 0 in here because there is no term with just plain old x. With synthetic division, I got 0 to be the remainder, so I could rewrite this as x minus 1/2, because I know that positive 1/2 is a root, times 2x squared minus 8x minus 4, and that's based on this part of synthetic division. To keep factoring, I would look at this piece right here, but the more I work with it, the more I'm going to see that it's not factorable, but we can use the quadratic formula. First I'm going to do, though, is factor out a 2 as a common factor in that part, because it is going to make your life a lot easier. And then now we set up your quadratic formula to solve this part. You probably got this far when you were using the quadratic formula, but if we keep simplifying, we're going to get down to 2 plus or minus the square root of 6. This is what the irrational root theorem was talking about, is that the plus and the minus version are both roots. So going back up here to the top, I know that x equals 1/2 is a root from what we already did there. And then 2 plus the square root of 6 is going to be a root, and 2 minus the square root of 6 is going to be a root. So there's the 3 roots of that problem. This one, again, is not real nice to factor, so I graphed it just to get us started. There's some icky decimals there, but there is one nice one of -1/2. Okay, so I did my synthetic division. I ended up with this. So I have x plus 1/2 is one factor based on that root, and then this is the rest of it. And from here, we're going to use the quadratic formula on this to find the other 2 roots. Again, let's factor out 2 just to make our lives a little bit easier. Okay, with the quadratic formula, I started here. I'm this far, so see how you're doing. Keep going, try to simplify that all the way. As I keep simplifying, I got all the way down to 1 plus or minus the square root of 5. So that means my 3 roots are going to be x equals -1/2. We found that from the graph. And then 1 plus the square root of 5 and 1 minus the square root of 5. And those were the ones that showed up as decimal approximations on the graph.